In this video, we're going to look at a few more examples of solving conservation of momentum problems, right? So either things bouncing, things sticking together, or things starting at rest and exploding, right? Those are our three main examples. So here's our first problem, right? This is an example of a sticking collision. I have a car that's going to be at rest, and another one's going to crash into it, and they're going to stick together. And I'm trying to find out what's the total speed of everything afterwards, right? So first step, most important, draw a picture. So let me draw that. Okay, so here's my setup. Before, I have one empty car traveling towards this loaded light one. And afterwards, they stick together and they're going to move off together with some unknown velocity, right? So I need to figure out what that velocity is. So again, the whole concept is the momentum before has to equal the momentum after. So over here, there's a total amount of momentum going this way. That means afterwards, it's got to have that same amount, right? So if I write my equation for each separate thing, then I'll be able to solve it, right? So I have two things over here. So I'll call this car 1 and car 2. So I have M1 V1 plus M2 V2. That's my initial momentum. Equals afterwards. So afterwards, notice these things are stuck together. So car 1 and car 2 are together. So I'll call that M1 plus M2 times my final velocity. That's what I'm trying to figure out, right? So now that I have this set up, let me just go plug in numbers and solve. So there's my solution. So M1 V1, M2 V2, it's this, right? Here it's the sum of both cars, but there's no velocity, right? It's not moving, so this one doesn't contribute any momentum to the system. So it's basically just the momentum of car 1. Equals, afterwards, all of this is stuck together, right? So it's this plus this plus this. So all of those times my final velocity. That gives me 27,000 equals 73,000 times final. And then I can divide over, and I get a velocity of 0.37 meters per second, which makes sense because this thing is hitting something that's getting a lot heavier. So it should get a lot slower in order to conserve momentum. Okay, so here's my second example. This one, if you look at it, I have a thing that starts together. It's a boy on a sled. And then as it goes, it's just a cart. Boy on the cart goes, and then the boy jumps off the cart, and now I have two separate things. So it's kind of like the backwards version of a collision where they stick together, right? So again, start by drawing a picture. So here's my problem drawn. I have the boy on the car going 2 meters per second, and afterwards the boy jumps off, he stops, the car keeps going. So let's figure out how fast the car is going at the end, right? So right here, this boy doesn't have any momentum when he jumps off, right? So the momentum is going to be 0. So it's really just this equals the car at the end. So I have the mass of the boy plus the mass of the car times my velocity of everything equals afterwards. I already said my boy doesn't contribute anything because his velocity is 0, so it's just the mass of the car times the velocity of the cart, right? So let me go plug in and solve. So my velocity of the car should be 4.8 meters per second afterwards, right? Which makes sense because it was heavy, right? The boy jumped off, so now the cart is going to be going faster, right? And because that boy didn't contribute anything, that's why this thing sped up, because its mass had gotten smaller. Okay, so here's our last example. In this case, this is like a bouncing collision, but it's a little bit different because I'm shooting an arrow at a watermelon, right? But the arrow is going to fly through the melon, and the melon's going to go, and the arrow has gotten a little bit slower, right? But everything's going in the same direction. So because it's not changing direction, it's still kind of easy, right? But same thing, before we start anything, draw a picture, right? So here's my picture. Okay, so here's my picture. I have my before with the arrow moving, and I have the after with both of them moving, right? So I want to solve for this velocity of the melon. So let me go write my equation for this. So it's momentum plus momentum equals momentum plus momentum. So here's my equation. I have the momentum of the arrow plus the momentum of the melon before equals the momentum of the arrow after plus the momentum of the melon after, right? So got my equation. That's the hard part done. Now I can just plug in all my numbers. So my velocity of the melon is going to be 0.3 meters per second, right? And that makes sense because the arrow's slowed down, but now I've made this 2 kilogram melon start moving too, so it's going to be small. These two momentums add up to the initial two momentums, right? So those three examples, solving any of them, right? The thing to do, pick out what type of a collision it is, right? Is it a bouncing collision where they bounce off and I have to keep them separate? Is it a collision where they stick and then I get to add the masses? Or the easiest case is in an explosion where it starts at rest, and then when they separate, those two momenta have to be the same, right? Once you do that, it's just a matter of plugging in the numbers and solving.